Hello everyone, I am Dr. Shweta Sharma from ABES Engineering College. In this lecture, I'll be discussing about the proton NMR spectroscopy. The content I will discuss in this lecture is principle of NMR spectroscopy, number of signals in proton NMR spectroscopy, chemical shift, shielding and deshielding phenomena, spin-spin coupling, reference compound in proton NMR spectroscopy, solvent used and selection rules for NMR spectroscopy, instrumentation and applications of NMR spectroscopy. Principle of NMR spectroscopy. NMR is the branch of spectroscopy in which radio frequency waves induce transitions between magnetic energy levels of nuclei of a molecule. Nuclei with a spin quantum number I greater than 0 show nuclear magnetic resonance phenomenon, and the proton has I value of 1 by 2. And in case of proton, it is known as proton magnetic resonance. Proton behaves as a tiny bar magnet, it having both electric and magnetic field associated with it, having magnetic moment nu. Proton has I value of 1 by 2. Therefore, it can show 2I plus 1 orientation. That is, the magnetic moment of proton can show 2I plus 1 orientation, which means it can show two orientations or two alignment. These two orientations are known as alpha state and beta state. These alpha and beta state represents the alignment of the magnetic moment of the proton. When there is no external magnetic field, these proton or these magnetic nuclei or the proton align themselves in without any separation. But when external magnetic field is applied in presence of field, these two orientations differentiate themselves and they get separated by energy gap delta E. The low energy state is known as alpha state and high energy state is known as beta state. In low energy state, magnetic moment of the nuclei is parallel to the external magnetic field. This is the direction of the external magnetic field. So in the alpha state, these magnetic moment of all the nuclei is aligned or parallel to the external magnetic field. Whereas in the beta state, the magnetic moment of all the nuclei of the protons is opposite to the or opposed to the external magnetic field. When alpha state changes to beta state, this is known as flipping. This flipping of state from alpha to beta takes place when these magnetic moment or these magnetic nuclei absorb the energy. This is the delta E, change in energy or the difference in energy from alpha state to beta state. Magnetic nuclei absorb this energy delta E or this amount of energy and flip their state from alpha to beta state. At this very moment when flipping occurs, NMR spectrum is recorded. Number of signals in proton NMR spectroscopy or equivalent and non-equivalent protons. This differentiation of equivalent and non-equivalent protons depend upon the different electronic environment present around the protons in the molecule. For example, this molecule has one set of proton because the electronic environment around this CH2 group and second CH2 group is similar. So all these four protons are identical in the NMR spectrum or proton NMR spectrum because electronic environment is same around these protons. But when this molecule, if we take this molecule here, we have the two set of protons. Methyl proton will give the signal different from the CH2 protons because now the electronic environment in the molecule is not symmetrical. Similarly, in this molecule, that is ethanol, we have three set of protons which are marked by A, B, C to differentiate them as three set of protons because all the three set of protons are different due to the difference in the electronic environment around these protons. All these set of protons are different from each other due to different electronic environment. This ether molecule has again three set of protons due to different electronic environment around all the three set of protons. In this way, we differentiate magnetically equivalent or magnetically non-equivalent protons. In the first case, in the first example, that is in the 1,2-dichloroethane, we have the all protons magnetically equivalent. Whereas in the second molecule, we have there is two set of protons, both are magnetically non-equivalent. In case of ethanol, there are three set of protons which are magnetically non-equivalent, and in this ether molecule, there is three set of proton which are non-equivalent or they are magnetically non-equivalent. Chemical shift. Chemical shift in the proton NMR spectrum is defined as the shift in the NMR signal of the proton of the sample compound with respect to the reference compound of the NMR. If we have the molecule, for example, ethanol, I have just discussed that there are three set of protons in the ethanol molecule, which are marked A, B, and C. When the NMR spectrum is recorded, it is recorded with reference by taking the reference compound TMS. This reference compound will give the signal. Then we have the three different signals. One signal of the OH, this represents the OH signal. Then we have the signal of CH2. Then we have the signal of methyl protons. These three signals shows the presence of three set of proton in the given molecule. This is the signal of molecule set of proton A. This is the signal of B set of proton, and this is the signal of C set of proton. Now we can see that with reference to TMS, there is shift of signals of methyl as well as methylene proton and the hydroxyl proton. This shift in the signal with respect to the TMS is known as the chemical shift. So, all the three set of protons have shown their chemical shift with reference to TMS. This is known as the chemical shift. Likewise, for other molecules, we can also explain this type of shift with reference to TMS. Shielding and deshielding effect. In an external magnetic field, electrons around the proton are induced to circulate and they produce secondary magnetic field or induced magnetic field. When this induced magnetic field is opposite or diamagnetic to the external magnetic field, the net magnetic field experienced by the proton is less than the external magnetic field, and thus proton is said to be shielded. This is known as shielding effect. And when the induced magnetic field is parallel or aligned to the external magnetic field, the net magnetic field experienced by the proton is more than external magnetic field, and the net field experienced by the proton is more than the external magnetic field, and in this case, proton is said to be de-shielded and it is known as de-shielding effect. Spin-spin coupling or multiplicity of the signals in the NMR spectrum. Spin-spin coupling means coupling of the magnetic moment between the neighboring protons. This phenomena is responsible for the splitting of signal of proton in the proton NMR spectrum. And this splitting is n plus 1, where n represents the number of proton on the neighboring carbon atom. For example, in this molecule CH3CH2Cl, there are two sets of proton A and B. Signal of A will be splitted due to the neighboring proton CH2 or neighboring protons B, and signal of B will be splitted due to the presence of neighboring proton A. And this splitting will be n plus 1, where n represents the number of proton on a neighboring carbon. Therefore, for the A signal, splitting will be 2 plus 1. This is 3, and this 3 is represented as triplet in the NMR spectrum. Signal of CH2 or B set of proton will be splitted due to A, and this will be 3 plus 1, which means 4. This 4 will be represented as quartet in the NMR spectrum. One more example. In this ether molecule, there are three sets of protons A, B, and C because of non-similar or asymmetric electronic environment around the protons in the molecules. These set of protons will be splitted due to the neighboring protons. A signal will not be splitted and it is observed as singlet in the NMR spectrum. B set of proton will be splitted due to the C protons or C set of proton, and C is 3, therefore it will be 4, and B set of proton will be represented as quartet in NMR spectrum. C set of proton will be represented or will be shown as triplet in NMR spectrum. Reference compound in proton NMR spectroscopy. Tetramethylsilane is used as reference compound in proton NMR spectrum, and it is used in very less amount of 0.01% to 1% amount. All the 12 proton of TMS are magnetically equivalent. This is tetramethylsilane having 12 protons, and all 12 protons are identical, marked as A set of proton. These 12 protons are highly shielded and they give the signal at delta scale of 0 due to the plus I effect of the silicon towards the methyl group. TMS has low boiling point and it can be easily recovered from the sample without destroying the sample. It is a chemically inert compound and easily soluble in organic compounds or organic solvents. Therefore, TMS is used as reference compound to determine the chemical shift in the proton NMR spectroscopy. Solvents used in proton NMR spectroscopy are chemically inert. There should be no hydrogen present in them. They should be magnetically isotropic and dissolve the sample easily. The most common solvent used in NMR spectroscopy is deuterated dimethyl sulfoxide and deuterated chloroform, that is CdCl3, and another common solvent is carbon tetrachloride having no hydrogen or no proton in it. In this way, these are the common solvents used for proton NMR spectroscopy. Selection rule for NMR spectroscopy is that all the magnetically active nuclei with spin quantum number value greater than 0 or not equal to 0 will be NMR active. This value should be greater than 0. They are NMR active nuclei. For example, proton or hydrogen atom is NMR active because it has spin quantum number value I is 1 by 2. Deuterium has spin quantum number value is 1. Tritium has spin quantum number value 1 by 2. Carbon 13 has spin quantum number value 1 by 2. Nitrogen 15 has I value 1 by 2. Fluorine 19 is again an NMR active and it has I value of 1 by 2. These are some common magnetically active nuclei with spin quantum number value I greater than 1, and they show nuclear magnetic resonance phenomenon. Instrumentation used for NMR spectroscopy is an NMR spectrophotometer, which consists of a stable magnet to produce a homogeneous field, a radio frequency transmitter, and a highly sensitive radio frequency receiver, a console to control the radio frequency pulses and convert the signals into the digital format, and a high-rated software for the data interpretation. Some common applications of NMR spectroscopy is that it is used to determine the structure of organic molecules. It is used to detect the purity of samples, to study the ketoenol tautomerase, and to perform the MRI of the body parts. Now let's take some questions of the magnetically equivalent and non-equivalent protons in the NMR spectroscopy. We have this molecule, this unsaturated molecule. This molecule has two sets of proton. Methyl proton represent A and these hydrogens represent the B set of protons. Because the electronic environment is same around these methyl proton, and for the B set of proton, the electronic environment is same. Therefore, these two hydrogens are similar and these two methyl groups are similar. So, this NMR or this compound will show two signals in NMR spectrum. Another example similar to this, here we have the molecule with chlorine substitution. Now, due to the presence of this chlorine, the electronic environment is not similar. Now, all the three hydrogens are not identical and they are A, B, and C. This molecule will show three signals in NMR spectrum. Another example, due to the presence of bromine atom, now all the three protons are not same and they have non-symmetrical electronic environment in the molecule. And there will be three signals in the NMR spectrum for this molecule. One more example, this is cyclobutane. In cyclobutane, all the CH2 groups are identical. All protons are same. This compound will give one signal in NMR spectrum because all the hydrogens are same. These are the references. Thank you, all of you.